Today, we continue with 4.3 and 4.4, which is all about logarithms and how they are related to exponentials. And I'd like to start today with doing one of the things I'm very fond of doing, and that is going back in time and showing you something you already know how to do and relating it to something new we're going to be learning how to do today. So here's a little cloud, everyone, and in this cloud I'm going to put three numbers, 12, 3, and 4. And what you're supposed to do with these three numbers, and as I said, this is going to be something you already know how to do, so don't worry, I'm not trying to insult anyone, I'm just building up to something, is you're supposed to use those three numbers to write both a division problem and a multiplication problem. And you should be able to do it because I specifically picked those three numbers and because multiplication and division are inverses of each other. So there are a couple ways to do this, everyone. If you're thinking there's multiple right answers, there are. But what you're supposed to do is you're supposed to use 12, 3, and 4 to both write a true multiplication statement and a true division statement. So what would be our true multiplication statement that we could write? 3 times 4 equals 12, and what would have worked just as easily? 4 times 3, of course, yes. And what can we write for the division statement?
12 divided by 3.
12 divided by 3 equals 4. Or, of course, 12 divided by 4 equals 3. All right, the reason that works is because multiplication and division are inverses of each other. So here's what I want you to do now. I want you to use these three numbers, 2, 3, and 8, to write a true exponential statement and a true logarithm statement. So you can also use those to write a true exponential statement and a true logarithm statement, 2, 3, and 8. And since we learned exponentials first, that one's usually a little bit easier, but because these are inverses of each other, both are completely possible. For instance, what would you do for the exponential statement? You'd write what to the what equals what?
2 to the third equals 8.
2 to the third equals 8. Very good. And down here we want to use those same three numbers to write a logarithmic statement, which we can do. Who knows what goes in this little box down here? Say again?
2.
The 2 goes down there. What goes here? 8.
3.
And then the 3 goes there. That's exactly right. And the way you can do this, the way you can remember this, is you can remember this. This is how I do it anyway. The base is the base. In other words, whatever the base is in the exponential statement needs to also be the base in the logarithmic statement. 2 and 2 in this case. And the other thing you remember is the logarithm equals the exponent. The logarithm is asking for the exponent, so the logarithm needs to be equal to the exponent. That's how I know, since 3 is the exponent up here, that this whole thing has to equal 3. And using those two statements, I can actually remember how to do this, how to go between exponential and logarithmic. And that's one of the things we need to be able to do. Part of being comfortable with exponentials and logarithms is being able to go back and forth between the two very easily. So, everyone on your own, without anyone saying out loud what it is, I want you to do this one again, this game again, but I want you to do it with 4, -2, and 1/16. So go ahead and write both an exponential statement and write a logarithmic statement using those three numbers. And if you're stuck, remember, whatever you use for a base, you have to use as a base in both places. And remember, the logarithm is equal to the exponent. So go ahead and write those on your own, on your paper, before anyone has a chance to shout them out and stop you thinking, especially me. Because we can just as easily use those three numbers to write an exponential statement as a logarithmic statement, just like we could just as easily use three numbers to write a multiplication or a division statement. The cool thing about these is that there is only one correct way. unlike the division and multiplication one where there were a couple answers, there's actually only one correct way to do this. What'd you use for your base class? 4, which means you put a 4 here and you put a 4 there. What was the power you put on 4? -2, which means you put a -2 here and you put a -2 here. And then 4 to the -2 is 1/16, and log base 4 of 1/16 equals -2. And that is the only correct way to fill it out for this problem. If you made a mistake and you understand your mistake, that's fine. If you made a mistake and you don't get your mistake, I would love to help. So sometimes they don't actually do this. This is a problem that I kind of made up with the cloud. I thought it was kind of fun to start this, but often what happens is you are told to convert from one form to another. So I'm going to make a couple little columns here if you want to do it, and each column is going to have 4 rows in it. We're going to have the logarithm column, and we're going to have the exponential column. And what I'm going to do over here is I'm going to write an exponential statement. Then over here I'm going to write a logarithmic statement. And then over here, I will write another exponential statement with the letters B, C, and A. And over here, I will write a logarithmic statement with the letters M, N, and P. Your job during this part of the lecture is to convert the exponential one to its equivalent logarithmic statement, and to convert the logarithmic statement to their equivalent exponential statement. So rather than me just giving you 3 numbers and saying doing both, I'm giving you one and you have to make the other. So go ahead and see if you can fill in this table. So if we remember that the base is the base, whatever the base of the exponential is has to be the base of the logarithm, and the logarithm is always equal to the exponent. What's this first one going to be? Log base, what?
4.
Log base 4 of 64 equals 3. Awesome. That's exactly what it is. That's the only correct answer. This one over here has to be an exponential. What's the base going to be? To what power? Equals. Awesome. Those two, you could have maybe gotten away with just knowing what numbers made sense. Down here, you actually have to know where everything goes. So what's the base on this one? B. So log base B of what? A equals C. Why? Because the base is the base and the logarithm equals the exponent. Down here, the base is the base is M. The logarithm equals the exponent, so what's the exponent? P equals N. It's important to be able to go back and forth between the exponential form and the logarithmic form. Because what this will allow us to do, well, let me just say this. Going from logarithmic form to exponential form allows us to solve for x in a new type of equation. Last time we learned a technique for solving for x by making the bases match. Today, we learn a new way to solve for x by being able to go from logarithmic form to exponential form. I will show you. This looks like a disaster to solve for x. Why? Because it's a new type of equation. We haven't solved for x in anything that looks like this before. But the secret for solving for x in this is to rewrite it in exponential form. Exactly what we were just doing, everyone. So we're going to rewrite this in exponential form. And if I want to do that, can someone tell me what the base is going to be? 2. Can someone tell me what the power is going to be? 4. And that's going to equal what? X plus 1. 2 to the 4th is 2 times 2 times 2 times 2. I get 16 when I do that. I subtract 1 from both sides, and I get x equals 15. This doesn't have to be a disaster, but it's a horrible problem if you don't remember to rewrite it in exponential form. Let me show you this. This is called the big mistake. What I'm about to do here is a disaster. You should never do what I'm about to do. I think I'll divide both sides by log base 2. That gives me x plus 1 equals 4 over log base 2. Subtract 1 from both sides. Not only is that wrong, it actually doesn't mean anything, everyone. You can't divide by log base 2. Dividing by log base 2 is like dividing by parentheses. It's a mathematical notation. It doesn't make any sense. This over here is just as bad as this. If I had 4, 3, let's see here. Let's make this 4 times 3 times x equals 7. And if I said, I think I'll divide both sides by that. I mean, that doesn't make any sense. Everyone see that? That's complete nonsense. You don't divide by parentheses. But that's what I tried to do. But that's something, I think this is 43. This is complete garbage. You cannot do this. It's trash. It's no good. It's not math. So, the secret, though, is if you are trying to solve for x and you have x mixed in to a logarithmic expression equal to a number, you rewrite in exponential form. Now that's very wordy, everyone, but that's exactly what we just did. If you're trying to solve for x, and you have x mixed into a logarithmic expression equal to a number, rewrite it in exponential form. That's exactly what we just saw. We're trying to solve for x. We had x mixed into a logarithmic expression equal to a number. And how do you solve that? You rewrite in exponential form. That is the way to do it. Otherwise, you lose. So, if someone says solve for x, and they give me these two problems here, in both cases, what I have is I have x mixed into a logarithmic expression equal to a number. Does everyone agree with that? In both of these situations. So my first step for both of them is to rewrite both in exponential form. Anything else you try is not going to get you anywhere. You're just going to be spinning your wheels. So, everyone, even though it doesn't look like a typical base because we're trying to solve for x, what is our base over in this one on the left? X plus 2, that's okay. What's our power? 1, and that should equal 15. This one over here, what's our base? 5. What's our power?
1.
Negative 2 equals x. So this one, anything to the first power is just itself. Subtract 2 from both sides, I get 13. It's over, I win. This one over here, it's practically done. I just need to rewrite 5 to the negative 2. 5 to the negative 2. The negative will flip it over. The 2 will square. What will it become? 1 over 25. Those problems will give you a big headache unless you remember what you're supposed to do. And what you're supposed to do is this. You see something like this, then you rewrite it like this. That's the secret. All right. Now, this did not come up on the problems I did. I specifically started us out with problems that this did not come up. But check this out. This is a really big deal for this type of problem. And you don't need to backtrack because I took care of it on these problems. I didn't start us out with this, but this is a big deal. Whenever your equation starts with a logarithm and you solve for x, you need to check your answers. Not because you're not good at math and not because you necessarily made a mistake, but because you can just naturally get a mistake. That sometimes happens. Did you ever solve an equation for x when you squared both sides? And then you had to go back and check your answers, and even though you didn't do anything wrong, you could get a bad answer? It's actually the same thing that can happen here. So what happens is, when you're all done and you have your x value, when you're done, you need to make sure that putting that back in the original equation does not give you an invalid base. You need to make sure you're not trying to make the base be something it can't be. And you need to make sure that it's not saying you're taking the logarithm of 0 or a negative number. You don't need to check everything. You don't need to go through the whole entire problem again. You do need to make sure that neither one of these things is happening. And this has not happened yet. And actually, I'm going to remind you about this again, because we're not going to see this again for a little while. But just remember, there are problems where you have to check your answer when you're done. And when do you have to check it? When it starts with a logarithm in it. As I said, I just want you to kind of keep that in your back of your mind, because we will get to that a little bit later. But I want to leave this topic alone for now. So this is just kind of like, remember this, I'll remind you about it again later. Okay. All right, everyone. This doesn't have a base 10 or e, but we don't need a calculator to do this one because we understand the question. This is asking what power you would put on a 2 to get the 4. What power would you put on 2 to get 4? 2. We can get the answer for this. This one does not require a calculator. This one just requires our brains and our understanding. What power would you put on 2 to get it to turn into an 8? 3. Remember, you're not multiplying, you're multiplying 2 by itself that many times. So we're not talking about 2 times 3, we're talking about 2 times 2 times 2. So this is going to be 3. And if you want, you just kind of want to remember why you got that answer. It's because 2 to the third is equal to 8. Now this one right here, the only way you could solve that in your head is if you didn't belong in this class, because you would be smarter than me. Because I don't know what power I put on 2 to get 5. I do know this. Because 5 is in between 4 and 8, the answer is between 2 and 3. But I actually don't know what that is. And here's the problem, everyone. Most calculators, I'm not saying your calculator, because I've seen a couple that don't. Most calculators have base 10, which is a button that looks like this, and base E, which is a button that looks like this. Many do not have a button that looks like this, where you pick your own base. Many do not have that button. Some do. I've talked to some of you who have that button on your calculator, but most of us don't have that. I don't have that on my calculator. So for us, we're kind of up the creek because we don't have a button on our calculator that lets us do this. Now everyone, what I'm going to do is I will give you a formula which I can't prove until later. Possibly later today, most probably next Tuesday. I'm going to give you a formula, and for now I'm going to ask you to trust me that this formula works, because it does, I promise you. And I don't like to give formulas without giving you some justification of where they come from, but this one we're going to have to go just on faith for now and then come back to it later to prove it. Does that sound okay to everyone? So here it is. It's called the change of base formula. And it's very, very slick. Thank you very much. I don't know what people can be so happy about there in school. It's called the change of base formula, everyone. And what the change of base formula allows us to do is it allows us to change any base logarithm to any other base that we want. If you look at this, what happens is you have a logarithm with some base that you're trying to do, maybe like we do. And what you can do is you can change it to any base you want. You pick the new base. And you can actually pick any base you want, which is why I wrote an A here, because that A can be any valid base you want. However, what most people do is they pick either base 10 or base E, because those are the two their calculator can do. So here's the punchline, everyone. Log base 2 of 5 can be rewritten as log of 5 over log of 2, or it can be written as ln of 5 over ln of 2. And I promise you, if you try both of those on your calculator, you will get the exact same answer. You will probably on your calculator, however, have to use parentheses. You will probably have to do this on your calculator. And a lot of them put a parenthesis automatically around the number you're taking the logarithm of. So you're probably going to be looking at something like this on your screen if you do this. And of course, I'm inviting you to do that right now. But this should give us the log base 2 of 5. And you can tell if you're right, everyone, or you can tell you have a good chance of being right, because if you do this correctly, you should get a number between 2 and 3. You should get 2 point something. What are you getting there? 2 point?
2.322, that's what I'm getting.
Oh, yeah, there it is. I'm sorry, I couldn't find it on my notes. You're absolutely right. Yeah, good. Yeah, 2.3219. I got up to 4 decimal places. I think that's what the computer usually asks me to do. That's why I do that, everyone. I think usually homework wants 4 places, which is why I usually do 4 places in the notes. So, everyone, that right there is the approximation of log base 2 of 5. And in case anyone's curious, I'll put the book one up here also. This is the books. And they kind of have some of the extra little details in there. What they don't bother to tell you is they don't bother to tell you that the two most useful to turn it into are both base E and base 10, because those are the two you can do on your calculator. But pretty much every time we use the change of base in this class, we go to base 10 or we go to base E, either LOG or LN, so we can do these on our calculator. So if someone asks me to do log base 34 of 2094, it is completely arbitrary if I want to change this to base 10 or base E. The question is, which one of these is it? The first one or the second one? Which one of those is correct?
The first one.
The first one. And in case you have trouble remembering that, in case you have trouble remembering it, I have a very childlike way of remembering it, but it works for me. I remember tiny little 34 goes below and mighty 2094 on top. Yeah, this thing's already headed downstairs. And it's childish, but it works for me. It's already headed downstairs, this one's already headed upstairs, so that's how I know how to do it. This would also be just as good. This would also be just as good. There's absolutely no reason that you can't do this one also. You can either do ln or log. There is absolutely no difference between these two. And we'll learn later why there's no difference between the two. But either way, what you are looking for is you are looking for the exponent you would put on 34 to get 2094. That's what we're looking for. That's what a logarithm is asking for. It's asking for the exponent that makes this turn into that. And it's
1684.
I did 8.5. Is that right? 8.5?
Yeah, the next
Okay.
7.
Yeah.
All right, cool. And this works even when you don't need to use it, which is pretty wild, everyone. Look at this. Look at this. I like this one a lot. You don't need to use the change of base for this one because my brain tells me what power I would put on 4 to get 64. What would I put on 64 to get 4? 4 times 4 times, how many times do I need to multiply 4? 3. But this is interesting, everyone. If you did ln of 64 over ln of 4, actually I'll do this. It doesn't matter what I do, but since my notes, I did it one way, I'll do it the same way I did my notes. If you do the log of 64 over the log of 4, what you actually get is something approximately equal to 1.806 179974 all over 0.602059991. No one bothers to write down this step, but when you divide this by this, assuming that I didn't round it, assuming he's going forever and ever and ever, what do you get? You get 3. So mess over garbage actually equals 3 exactly. So even if you flipped out and you're like saying, oh, I don't remember how to do that one, I think I'll use the change of base formula, you can still get the right answer as long as you don't round partway through. That's the change of base formula, everyone. That's how we do logarithms other than base 10 or base E on our calculator. It does not matter which one you do, but you cannot mix. In other words, class, you cannot do this. That won't work. You got to pick one and use it. All right, very cool. So, let's say someone told me to graph a logarithmic function. And I kind of freaked out and I'm like, wait a minute, I don't remember how to graph a logarithmic function. I know we kind of talked about what the graphs looked like last time, but I don't really remember. What do I remember? Not a lot, shoot. But what I do remember is I do remember the inverse of f of x equals log base 2 of x is the exponential function 2 to the x. Do I remember that? Are inverses and logarithms inverses of each other if they have the same base? That's something we want to keep on remembering over and over again. That's not going to go away. We want to keep on remembering that. Logarithms and exponentials are inverses of each other as long as the bases match. Keep that in your head always throughout this unit. So here's what I remember, everyone. I remember they're inverses of each other, and I made this for myself. And here's what else I remember. It is easier to plug numbers into an exponential than it is to plug numbers into a logarithm. For instance, if I come over here, and I want to get some points that are on that graph right there, I can plug anything I want because this exponential has a domain of negative infinity to infinity. So I plug in -2, -1, 0, 1, 2. Maybe I even plug a 3 in there, just for grins. And I can take 2 to all these powers, because what's 2 to the 0th, everyone? 1. What's 2 to the first? 2 itself. What's 2 to the -1? 1/2, itself flipped. Squaring it is 4, -2 is squared and flipped, and 3 would be 8. And just like that, I get 6 ordered pairs, because it's very, very easy, relatively, to find ordered pairs on an exponential like that, because you can plug anything you want in. But that's not what I'm trying to do, everyone. I am trying to graph this sucker right here. That's the one I'm trying to graph. I'm trying to graph f of x equals log base 2 of x. I need a bunch of ordered pairs over here. But secretly, do I really have those ordered pairs now already? Yeah, because can someone tell me the first ordered pair I can write over here?
-2.
1/4 -2. I've got them, I just need to flip them around. 1/2 -1, 1 0, 2 1, 4 2, 8 3. And the reason this is a good technique, is because most people, when they approach a new function, don't say, oh, I think I'll plug 1/4, 1/2, 1, 2, 4, and 8. That will give me the ordered pairs I need. A lot of people think I'm going to plug these in, which only works well with exponentials. But then we can swap them, and now we can graph a logarithmic function. So let's see what we got here. 1/4 -2. I know it gets a little bit tight down here with the fractions, everyone. And the reason it gets kind of bad down there with the fractions is because we have an asymptote, so everything gets very, very close together. But if I plot my points, I'll get that. I'll get the logarithmic graph, and now it looks familiar to me. I remember what it looked like. Does this thing have an asymptote? Does anyone remember what the equation of the asymptote is? Y equals x is the line we would flip over for a reflection. But what's the asymptote for this graph? X equals 0. Yeah, a lot going on. I know that, everyone. A lot going on. X equals 0. We got an x-intercept right here of 1, 0. I shouldn't write that in blue, because I'm trying to keep blue for the one we didn't graph. So what I graphed here, everyone, was I specifically only graphed f of x equals log base 2 of x. What I did was this over here, I used this just to get some ordered pairs for log base 2 of x. I didn't actually plot any of these points, everyone. I just used this table over here so I could flip it, reverse it, to get this table over here. Because it is not the most intuitive thing to most people when they first do these problems to think, I'm going to plug these numbers in. I'm not saying you don't know to do that. I'm not saying you can't figure that out. I am saying plugging in 1/4, 1/2, 1, 2, 4, and 8 is not as natural as plugging in -2, -1, 0, 1, and 2. Most people don't approach a new function and say, I think I'll plug some fractions in there just for fun and see what happens. But it turns out fractions give us exactly what we need. All right, class, what do you think about that? What did I just show you? I showed you how to use an exponential to get some ordered pairs on a logarithm. That's what this was. I think I'll write that. And I know graphing is always tedious, but I want to do a little bit more of it. Now I will use my graph and ordered pairs for f of x equals log base 2 of x to do some transformations. Now everyone, what I'm going to do is I'm just going to do a couple transformations. I'll use my graph and ordered pairs for f of x equals log base 2 of x to do some transformations. So, let's see here. We had 1/4, 1/2. Is that where I started up there? Yes. 1, 2, 4, 8. -2, -1, 0, 1, 2, 3. Okay. I just copied that order, that chart from up above. That's all that is. It's a copied chart from up there. Same one. No difference. What if someone chose to drop a 4 in front of that? What if someone chose to drop a 4 in front of that? What would we have to do to change my ordered pairs? Does anyone remember what that does when you multiply out in front by a number? Multiply the y's by that number. Very good. This is a vertical stretch. Multiply y by 4. This would not change the x values at all. What it would do is it would multiply all the y values by 4. It would stretch out the graph. We don't do a lot of transformations with these logarithmic functions, but we do enough of them or a few of them, so I do need to make sure that you've seen this before. All right, everyone understand that we can put a 4 out in front and multiply everything by 4 in the y column? We've done that before with different functions, but of course it's trickier when you're doing it with logarithms because they're brand new. How about this, everyone? I wonder if I can copy this and bring it down. Copy, I'll go to a new page is what I'll do. Edit, paste. Very cool. That'll save me a little bit of time. Okay, let's try this here. A little trickier. A little trickier. What's that going to do, everyone?
Add 3 to the final
Good.
result.
Shift it to the left 3. What'd you say over here?
Add 3 to the final result.
Not quite.
Well, to the
We are going to shift left 3,
yes.
but since that's a plus 3 that's on the inside, what are we going to do?
Negative.
We're going to subtract 3 from what? X or Y? It's on the inside. X. Yeah, so these don't change at all. But we do have to subtract 3 from all these over here. Now that might give you a bit of a headache when you're doing some of these because they're fractions, so let's see here. So that's going to be negative 11/4, I believe. Let me think about that for a second. It's going to be negative 2 3/4, so yeah, negative 11/4. Okay, yeah, it's frustrating. I had to even do some side work here. Maybe you have to run a calculator, that's okay. That's okay, but that's what happens. And what that's going to do, everyone, what that's going to do is it's going to take the entire graph and move it over 3 units. X equals negative 3. It's going to move the entire graph over 3 units like that. You do a little bit of this in your homework. You're going to see a little bit of this in your homework. That's why I wanted to show it to you, everyone. That is why I wanted to show it to you. Let's do one more. Let's do one more. I'll tell you, this actually isn't my favorite thing to do either. Oh my gosh, that is my favorite thing to do, though. Okay. Oh, for crying out loud. Edit, paste. Whole thing, please. Okay, good. Now, what I want to speak about before we do this one, I actually should have mentioned this on this one up here, is are we allowed to take the logarithms of negative numbers? Are we allowed to take the logarithms of negative numbers? No, we can't. Yet I have some negative numbers over here. How is that possible? It's because they get plugged in for x. And what happens to these numbers before you take the logarithm? What happens to them? 3 gets added to them. So, negative numbers can be plugged into a function with logarithms if they become positive before you find or take the logarithm. So it is okay that I plug those negative numbers in because before I ever took a logarithm, I added 3 to them. And therefore, I was only taking the logarithm of positive numbers still. All right, let's do one more of these and then let's walk away from this mess. Let's do this one right here. This one, for instance, might look really, really bad. You might say, Steve, you can't plug anything in there because you got a negative in there. But that's not true, because if I plug a negative number in here, this negative will make it positive before I take the logarithm. Does everyone agree with that? What this is, everyone, is it's on the inside. So this is a reflection over the y-axis, and we change sign on all x values. In fact, it turns out we can only plug negative numbers into this one. Because if we plug a negative number in, that negative sign that's waiting for it will make them all positive. So we plug in a negative 1/4, a negative 1/2, a negative 1, a negative 2, a negative 4, and a negative 8. All those get plugged in, and as soon as they get plugged in for x, they get hit with this extra negative sign, and that makes them all positive before we take the logarithm. Negative cancels a negative. And what this does, everyone, is it creates a graph that looks like this. Same vertical asymptote, new x-intercept, and a domain of negative infinity to 0. And let me write down the domain for this one. This one has a domain of negative 3 to infinity. So class, what's the punchline of these last 2 pages of notes? First of all, graphing is not that much fun, but what's the punchline? Is if you want to know some ordered pairs on a logarithm, it's usually best to start with an exponential. And then transformations work the same way they always have, which is not easy, but it still can be done the same way we did it before. So I would say, to find ordered pairs on a function of the form f of x equals log base b of x, find ordered pairs on b to the x, the inverse function, and swap them. Transformation rules of logarithms work the same way they did in unit number 1. It's a lot of information, I know. We'll do some more fun stuff that doesn't involve so much graphing when we get back from break, everyone. So it's important to know how to graph exponentials and logarithms, because that's what this chapter is all about, is these exponentials and logarithms. But I will say this. The 2 graphs that you're probably called most upon to draw after this in your future in mathematics are probably the e to the x graph and the natural log of x graph. These are probably the 2 biggest ones you'll learn about. Unfortunately, a little bit frustrating because e is an irrational number. But of all the graphs that I see on exponentials and logarithms, these are the 2 that I see come up the most in classes after college algebra. So make sure that you know these 2 graphs also, and know their basic shape, their asymptote, their intercept, so on and so forth, because these will come back over and over and over again as you make your way through the world of mathematics. All right. We know there are rules that allow us to alter mathematical equations and expressions. Also, there are things that we can't do. For instance, everyone, am I allowed to multiply this 2 by this 3x, multiply this 2 by this 5, and distribute it through? That's something I can do. That's a distributive property. We're definitely allowed to do that. That's cool. Things like that. Cool. How about this? Am I allowed to cancel these x's, make that 3 plus 4, and write it as 7? Can I do that?
No.
No, I can't cancel those x's because both terms on top don't have an x's. This is not a rule. This is not okay. You cannot do this. That's not all right. But sometimes we think something's a rule when it's not. How about this? It's very, very easy with all the mathematical rules to forget which rule is which. For instance, here's 2 situations. 5 squared to the 7th and 5 squared times 5 to the 7th. And it's very, very easy to forget which one of these situations do you multiply those 2 powers and which one do you add the 2 powers. What do you do with this first one? Multiply them or add them?
Multiply.
That's the one where you multiply them. This is the one where it would turn into 5 to the 14th. This is the one where it would turn into 5 to the 9th. So we've got our work cut out for us in mathematics remembering how to do these rules. And the reason I say all that is it's an introduction because we have 3 rules for altering logarithmic equations and expressions. And it is very easy to get them wrong. It is very, very easy when you're taking an exam for anyone to get these 2 rules backwards. Does everyone agree with that? Anyone can do that while taking a test. It's not because you're not smart. It's not because you don't know math. It's just because you know 2 different rules and sometimes you get them backwards in your head. So we're going to learn some new rules today for logarithms. But we have to pay very close attention to how they work so we don't make up a rule that doesn't exist. So we are going to learn the power rule, the product rule, and the quotient rule. And it's actually better to say the power rule, the product rule, the quotient rule of logarithms. And I'll tell you why. Calculus, which of course we're not doing in here, also has 3 rules called power, product, and quotient. Now, we're not going to worry about them getting confused in this class, but if you're talking to a friend who's a calculus student, which you probably have some friends that are taking calculus, and you tell them you're doing the power rule, the product rule, and the quotient rule, they might be doing them too, but they're doing them at different rules. So we are specifically doing the power rule, the product rule, and quotient rule of logarithms in our class. And that's all you have to worry about in this class. But I know sometimes some of you ask other people for help outside of class, and that's just fine. I just want to make you aware that these are used in other ways. All right, remember, for these rules to work, we need to remember a couple things. Remember, our base is always a positive number not equal to 1. Our base will always be a positive number not equal to 1. We only take or find, whatever you want to say. Some people say you take a logarithm, some people say you find a logarithm. We only take or find logarithms of positive numbers. So when I give you these rules, remember, anytime I'm talking about a base, I'm specifically talking about a positive number not equal to 1. And anytime I take the logarithm of something, I'm specifically only taking the logarithm of a positive number. Here are our rules, everyone. Well, here's the first one anyway. Oops, I covered it up. There we go. I made these myself, everyone. Power rule. Log base b of m to the pth power, ooh, that's fun to say, the pth, is equal to p times log base b of m. Another way of thinking that, everyone, is that this power can drop down in front, or it can move up there, like that. You can move that number around, either as the power on the thing you're taking the logarithm of, or the multiplier in front. So, let's see how this works, everyone. Log, actually let's do one we can do on a calculator. We'll do log base 10 of 3 to the 5th. Okay, class, this is something we might be given. According to the power rule, we can rewrite this like this. Those two things are supposed to be exactly the same. Which means, everyone, if on your calculator you do log of 3 to the 5th, or you do 5 log 3, or you do the log of 243, that's 3 to the 5th, everyone, all of these should give you the exact same decimal. It's a decimal. It's not a nice number. But they should all give you the exact same decimal. So if you have a chance, try a couple of those. Try the middle one for sure, and then try either the one above it or the one below it. But all of these should give you the exact same decimal, which we will round to 4 places.
Oh, my.
2.3856. If you're not getting that, please remember you are welcome to come see me sometime or see Rachel sometime, and we will definitely help you do that in your calculator. Remember, if you go to Rachel's session, it's okay just to pop in and say, can I have 5 minutes so you can help me with my calculator? And you can stay and ask more too, but you don't need to stay the whole time just for a calculator question. This is the power rule, everyone. We can bring the power down in front. The power can only come down in front if the power is on everything. That's why I put this right here, everyone. This is a very common error people make. That's a very common error people make. You see how that power there is just on the N, not on the M? It cannot go down in front. An example of that would be this, everyone. Here's something you cannot do. Because the squared was not on the 5x, it was just on the x. That's why you can't do that. This one you can do. I don't know what that stray little marker there. Don't let that bother you. Wish my pen didn't leak. That one is okay because the squared's on both of them. Everyone see the difference between those two expressions? So make sure you only use the power rule when you're allowed to use the power rule. All right. As of right now, that doesn't seem too interesting to us, but that will help us. I promise you, that will help us, everyone. The main way it's going to help us is something like this. The power rule can get variables down from the exponent. Natural log is 6 to the x power. Dealing with a variable that's up in a power is very difficult, but according to the power rule, I can bring that x down in front. So that's the main thing we're going to use it for in this class, is that the power rule can get variables down from the exponent. That's one reason it's so helpful to us in here. Okay. Logarithms do not distribute because you are not multiplying a logarithm. You are taking or finding a logarithm. I'll show you what I mean by this, everyone. I mentioned before there are rules that we try to make up that aren't real rules, and this is a big one that people think they can do. We put it in red because it's so bad and evil, and I never want you to do this. It looks like it should work, but it doesn't, everyone. Because you're not multiplying by logarithm, so it's not a distributing situation. You are taking the logarithm of x plus 15. So the log of x plus 15 is definitely 100% not the log of x plus the log of 15. The ln of x plus 4 is absolutely 100% not the ln of x plus the ln of 4. You may not do that ever, because logarithms do not distribute. This is what they do, though. This is what they do. And this is not distributing, everyone. This is a property of logarithms. That's not what I want. Go away. This is the product rule, everyone. And I even said in the rule itself, this is related to exponential rules. You are not factoring, you are not distributing. What happens, everyone, is if you have the logarithm of two things getting multiplied, then that is the logarithm of the first thing plus the logarithm of the second thing. This is not the distributing property. This is a logarithm property. And this one people get wrong so often that I actually took the liberty of writing 3 rules down there that are absolutely 100% not rules. None of these are things you're allowed to do. None of these. And it's amazing how tempting it is to try one of those things when you're trying to remember this rule. But the rule that you need to know is this one right here. That's the rule you need to know. And it's kind of cool how it works, actually. It's kind of cool. Check this out. Can someone tell me 2 numbers you multiply to get 77? 7 and 11? Okay. So this is the same thing as this. Everything I'm doing right here is legal, everyone. This is okay. 7 times 11. And according to the product rule, the rule that we just put up there, you are allowed to do this. Put those in parentheses so you don't get my ln confused with my 11. ln of 7 plus ln of 11. I promise you, class, if you take out your calculator and you do the natural log of 77 on your calculator, you will get the exact same horrible decimal that you will if you do the natural log of 7 plus the natural log of 11. They will give you the exact same answer. A horrible decimal that we don't want to deal with. But you will get the same answer. This is called the product rule, everyone. Is that the product rule?
Yeah, no.
That one's not. Is that the product rule?
Yeah.
That one is. They both look kind of good. So that's why it's very, very important to make sure you look at this rule and understand it. Okay, one reason this is so helpful to us is in Math 121, we often use this to turn several logarithms into one logarithm. This is how we use this in this class, everyone. I'll show you right now. Someone gives us something like that, log of x plus log of x plus 4. We rewrite it like this. That's how we're going to use it a lot in this class, by taking a couple logarithms and making it one logarithm. It's a very helpful trick. Because remember, even though you almost always see the product rule written in this order, it's an equal sum. So you can either use it to make one logarithm into 2, or for us, we're often going to use it to make 2 into 1. But it is very, very easy to make up a rule that doesn't exist. So watch that. Make sure you're not making up your own version of the product rule that isn't the real rule. We okay? We're going to use all these rules together in a little bit, everyone, but I just want to get them all out there. Last one is the quotient rule. This one I'm not going to say is easiest to remember. I will say I don't find people getting confused with this one quite as much as they get confused with the product rule. This one says if you are dividing whatever you're taking the logarithm of, so if you're doing the log base b of m divided by n, then you can break it up into two logarithms with a subtraction in the middle. This again is not like distributing or anything like that. So once again, you can't do a distributing with the minus sign. That's not how this works. The way this works is if you have something like ln of 48 over 6, you could either rewrite that as ln of 8, because 48 divided by 6 is 8, or you could rewrite that as ln of 48 minus ln of 6. And I promise you, if on your calculator, you do the ln of 8, or you do the ln of 48 minus the ln of 6, both of those will give you a horrible decimal, but they will both give you the exact same answer. So whichever way you write this, these actually all go together. All of these are the same thing. Whether you do on your calculator ln of 48 divided by 6, or ln of 8, or ln of 48 minus ln of 6, what do you get?
2.0794.
Great. And if you didn't bring your calculator with you today, make sure you're trying these when you get home, of course. Make sure you're trying to make sure you can do them on your calculator at home. And if you can't, you can talk to Rachel with me. All right, that's the quotient rule, everyone. We're not going to do a whole lot of practice with that right now, because I want to use practice when we can practice a bunch of them together. I will say, however, though, that you can actually use the product rule and the quotient rule together. So check this out, everyone. This is actually one of the more useful things to us, the fact that we can use these rules together. And they don't show you this in the book, but I find that I use this a lot. If you're taking a logarithm of some sort of fraction, you have a bunch of things multiplying on top and a bunch of things multiplying on the bottom, then what happens is you can break this up into a bunch of different logarithms. And what happens is everything that was multiplying on top gets a plus sign in front of it, and everything that multiplies on the bottom gets a minus sign in front of it. What this is, everyone, is it is a combination of both the product rule and the quotient rule working together. Look at my original fraction. M and n are on top. That's why they both become positive logarithms. P and Q are on the bottom. That's why they both have these negatives in front of them. This allows us to either rip apart or put together a logarithm. In fact, the words we use for that, everyone, the words we use for that you will see are expand and condense. Expand, turn one logarithm into many, and bring powers down in front. Condense, bring powers up, and turn many logarithms of the same base into one logarithm. Expand. Turn one logarithm into many and bring the powers down in front using the power rule. Condense. Bring the powers up and turn many logarithms of the same base into one logarithm. This right here, expanding, is a cool trick in Math 121 and very helpful in calculus. Condensing is very helpful in Math 121. You'll notice when you do the homework that there's not a really big practical application for being able to do expanding in this class. It's more sort of just something you need to know how to do. If you're like, Steve, why do I need to know how to expand this? I'll say to you, in this class you really don't have a lot of use for that, but you do need it for later, and it is part of the curriculum of the course. If you said, why do we condense it? I would say because in this class, Math 121, especially next week in Math 121, we're going to find it very, very useful to be able to turn many logarithms into one logarithm. So this is kind of the big one for us, condensing. But we should still expand. We should still know how to expand. So if someone told me to expand a logarithm, they might give me something like this. Log of 5x squared over 2. Now, does everyone agree that in the numerator of that fraction, I have 5 times x squared? And on the bottom, I have a 2. So watch this, everyone. Using the combination of the product rule and the quotient rule, I break this up into 3 logarithms. Watch this, everyone. I break it up into log of 5 plus log of x squared minus log of 2. Why do the log of 5 and log of x squared both have pluses in front of them? Because they came from the top. Why does the log of 2 have a minus in front of it? Because the 2 came from the bottom. What do they consider expanded? After you break it up into many logarithms, they consider it expanded once you also bring down powers. In other words, that x had a squared on it, and using the power rule, I can bring the 2 down in front. So this first step was done using product and quotient rule together. This one right here was done using the power rule. And that's what they consider an expanded logarithm. What's that for in this class? To get credit. Doesn't really have a lot of reason, like practical applications for us in this class. What's more useful to us is condensing. Something like this. You've got 2 logarithms there. What you want to observe first is this. Same base, because you can't condense them unless they're the same base. They must be the same base. They're both base E. And what did I say about condensing? Bring powers up and then turn many logarithms of the same base into one equation. Does one of these have a number in front of it?
Yeah.
Can we bring up that power and make it a power? Yeah, let's do that first. So the first thing we do is we bring that up like that. And then we turn it into one logarithm. What goes on top? X cubed, because it has an invisible plus sign in front of it. What goes on the bottom? 12, because that logarithm had a minus in front of it. So what happened here was we used the power rule. And actually what happened here was we just used the quotient rule. The product rule didn't really come up. We just used the quotient rule to do that last step. All right. So, class, how about this right here? Is that the exact same answer to the one we just did?
Because you have negative.
Look where the negative's in front of.
Oh, yeah, it's the same.
The same thing. So don't let it bother you if the negative one comes first. Don't let that bother you. So this, yep, same thing. Look at this one, everyone. Do you Do any of them have positives in front of them? Just put a 1 up there. Just put a 1 up there. If you said to me, Steve, how can you put a 1 up there? Because if I were to expand that, Steve, wouldn't I have to expand it like this? And I'd say, yeah, you would have to expand it like that. What's the log of 1? Try it on your calculator. Log of 1.
0.
0, doesn't matter. Everyone see why we can put that 1 up there, no problem? The log of 1 isn't anything. 0.
And those the power in the top.
What's that?
So we put the 1 in the top. So
The one on the top got a plus sign in front of it, but didn't matter because it was a 0 anyway. Like, I didn't want people to think that this was messing me up because I suddenly put a 1 up there, because if you were to go the other way, if I told everyone here to expand this to make it large again, you'd put a log of 1. And you'd be fine doing that, but you wouldn't need to put the log of 1 because the log of 1 is just 0. All right, cool. So, how about this? Is that right? Wrong. Because, good, when I expanded, I changed my base from 3 to 10, and that's not okay. Everyone see how easy it is to lose a base? Because you just want to write LOG and be done with it? But this one had a base of 3, and I needed to keep that 3. So, that one's not okay. This one would be. That's all right. Try this. If I tell you I'm not done yet, am I okay so far?
Yeah.
That looks okay to me. That's the product rule, everyone. The product rule can be used with as many as you want. Not just 2, but 3, 4, 5, 6, 7. No matter how many things you're getting multiplied. So, product rule works for as many multiplications as you need. It doesn't matter if I had 30 things getting multiplied in there, I could turn it into 30 logarithms. Am I done yet? No. And there's actually 2 reasons I'm not done. This right here is actually the only one that's done, and I'll tell you why. Powers must come down to expand, and logarithms that can be evaluated without a calculator must be simplified. Everyone, you do have to bring powers down, which I bet most of you caught. You do have to bring that 2 down in front and make this 2 log base 4 of y. The other thing, which I don't blame anyone for because I hadn't told you about it yet, is they do expect you, if it is possible to simplify a logarithm without a calculator, they do want you to do that. Now this did not come up on the previous problem, because I don't know what power you take 3 to get 8. Everyone cool with that? But do I know what power you put on 4 to get 16? What power do you put on 4 to get 16? 2. So I do need to write that as 2. And now it is done. They don't always tell you to do that either. That's what's so frustrating. But one of the things they do expect you to do when you simplify one of these is they say, if there's a logarithm that you can evaluate without a calculator, you do have to do it. So you do have to watch out for that. And it's annoying if they don't tell you to look out for that, but you do have to watch out for that. All right. Let's try a couple more big expanding problems here, everyone. And I want you all to try these. And it's okay if you make a mistake. It is 100% okay if you make a mistake, but I want you to try this. Everyone, I want you to try and expand that. And if you get a little frustrated, that's okay. I'm going to go ahead and write the first step up here. No one look up here until you're ready to check your first step. Now I'm going to finish it. And that up there is the final answer, everyone. That is the final answer. That's as much as you can expand it. I do want to address a few things. On the first step, what I did was I noticed I had 3 things getting multiplied on top and 2 things getting multiplied on the bottom. So 3 on top, 2 on the bottom means I get 5 logarithms. And the ones on the bottom get minus signs in front of them, the ones on top get plus signs in front of them. On my next step, I looked for any powers to bring down. The y cubed had a 3 that could come down in front. The z squared had a 2 that could come down in front. I also looked to see if I could evaluate log of 100 without a calculator. Since this was base 10, and I know that 10 squared is 100, that could turn into a 2. The other detail you want to make sure you have, for sure, is you do need these parentheses. These parentheses are needed, and furthermore, you cannot break that up anymore. There is no rule that allows you to break up this log of x plus 1. It must stay like this with the parentheses. So, with the exception of mine being in blue, yours should look exactly like mine.
And that's the final answer?
That is the final answer because we're just expanding it. As I said, in Math 121, this is more sort of a mathematical trick. If you said to me, Steve, what would we do with that? I would say, take Calc 1 and you'll see what you're going to do with that. In this class, I just want you to learn how to do it. We're making a toolbox for ourselves. All right, the next one we're going to try, I'm just going to give you some advice and then see how well you handle it. That's r to the 7th, everyone, and z to the 5th on the bottom. That's r to the 7th. Everyone, look at this one and look at that square root. Let's do the first step together. Can square root be thought of as a power? Can you rewrite square root as a power? What power is the same as square root? 1/2. Now here's the thing,
I
everyone.
always forget that.
That's okay, that's why we come to class, right? So we can remember. Here's the thing, I can rewrite this, but that 1/2 is a power on everything there. Which means that when you break this up into several logarithms, all of them need to have that 1/2 in front of them because that 1/2 comes down right in the beginning. So you have a choice. When you break this up into several logarithms, what you can do is you can put 1/2 in front of every log, and this one's log base 3, or you can do a 1/2 in front of a big set of parentheses. You can do either one of those things. Everyone expand that one for me. And you either need the 1/2 in front of everything with parentheses or in front of each individual one. Whichever one you think is easiest. I'm going to show you both answers. I'll show you both answers so you can do it either way. When all the dust settles, you should have one of the two answers I have starred there. You can choose to keep that 1/2 in front. I don't mind if you do that, that's fine. Or you can choose to distribute it back through, and that is fine also. One thing that's very easy to forget on this, and make sure you didn't forget it, is make sure you put a little base 3 on all your logarithms, because they're all base 3 on this problem. So, did you remember all base 3s? Was everyone able to get either one of the two answers I have starred on here? Or does anyone have a question or a comment they'd like to make about this? All right, cool. So, let's just take a little bit of a tease into what's going to be happening next in this class. Expanding is great. But here is where condensing will help. You see, class, one of the things we're going to have to keep doing throughout this whole unit, and probably for as long as you're taking math classes, is you're going to have to keep solving for x. Let me make sure I'm still recording. Yes. We got to make sure we keep solving for x. Now, this looks sort of similar to the problems we were doing near the beginning of class today, where we rewrote an exponential form. The problem is this. We can only rewrite in exponential form if we have a single logarithm equals a number. And in this particular problem, at this moment, do we have a single logarithm equals a number? So we cannot do that. But the product rule tells me that if I have log base 3 of 5 plus log base 3 of x, I can rewrite that as log base 3 of 5 times x. Does everyone agree with that? That is a condensing, everyone. That is turning two logarithms into one. And once I do that, I now have log base 3 of 5x equals 2. And now, since I have a single logarithm equals a number, I can remember this. Base is the base. Logarithm equals the exponent, or the power, and I can rewrite. If I remember that the base is the base, and the logarithm is equal to the exponent, I can rewrite this. What's the base, everyone? 3. What's the exponent? 2. Equals 5x. Awesome. Just like that, I turn into ah. Because what's 3 squared, everyone? 9. And to finish solving this for x, we simply divide by 5, and we are done. Now, class, I know you're eager to get out of here, and it is almost time. I am aware of that. But this is what I want to do before we go. So just bear with me for the last couple minutes here, because I still have 2 minutes left, and I want to use them. This is the original equation we started with. you might remember something from earlier in this class, where I said that there was a big warning. Oops, that doesn't help me. I'm running out of time. There is a big warning, everyone, which you don't need to read here because it's bigger in the other part of the notes. It says you must check your answer in the original equation to make sure that you are not taking an illegal logarithm and you don't have an illegal base. There is only one x right here. Is 5/9 a negative number? Then it's fine. Fine, because 5/9 is positive. And that means our answer stands at 5/9. I'm not talking about doing a 3-minute check. I'm talking about doing a couple second check just to make sure you got the right answer. This is where we're headed next week. You should be able to do some of your 4-3 homework, some of your 4-4 homework, but maybe not all of either one. But do what you can. And watch those due dates. Yeah?
So, kind of confused. So, wouldn't it be...
Everyone disregard the last few moments of the lecture. I made a mistake. Oh my gosh. The answer is actually 9/5. Thank you.
Hey, you're welcome.
And it doesn't matter because 9/5 is positive, and so our check still works. All is well, and I want everyone to have a good weekend. Thank you for pointing that out to me. All is well. Thank you very much.
Guys, you're welcome.